Alright, today I'm going to make a video about summations, and in order to make it as intuitive as I possibly can, I'm going to be using Legos to try to make some shapes and hopefully make it as comprehensible as possible. So I'll start off by just describing exactly what a summation is in the case that you don't know already. So a summation can look scary, and one of the reasons it looks scary is it has this symbol that we might not be used to. That's a pretty poor drawing of it, but that's a sigma. At the bottom and top, you have a bunch of other scary stuff. So let me give you an example problem. And in order to represent this, let's think of bowling. If you've ever gone bowling before, you know that there are 10 total pins you need to knock down. And they're configured in this way. And of course, if you get a strike, you knock all 10 down on the first try. Spare, you knock all 10 down using 2 tries. Neither of those things happen for me ever. But this is equal to this. That's all it means. This is saying what happens when we sum or add up, starting with the index of 1 and going by whole numbers up to 4. What happens when we add up 1 plus 2 plus 3 plus 4? And this is exactly what this is. We know that there are 10 pins in a bowling alley. And we can count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But that's all a summation is. Let's add up numbers from a point to another point. And sometimes summations can be a little bit more complicated. So let's say you did that, but instead of just being I, you wanted to do I squared. So that would be 1 squared plus 2 squared plus 3 squared plus 4 squared. Okay? And we'll talk about how to do that later. But for right now, let's stick with the basic. So I'm going to do 2 things. Number 1, I'm going to show you the standard proof for kind of the shortcut for figuring this out for big numbers. Number 2, I'll show you how to represent that with Legos. And hopefully by the end of this video, it'll be really, really common sense to you. It'll feel intuitive. You'll have a genuine understanding of how this works. So let's start out with a problem that might be hard to solve. Because from 1 to 4 might be easy. Even if we added a 5 on there, right? You could just take the 10 and add 5 to it. You'd know that 1 through 5 is 15. But what is it from 1 to 200? That's a little bit more complex, right? I mean, to do 1 plus 2 plus 3 plus 4 all the way up to 200 would take a lot of time. And so it could be kind of useful to come up with a way to do this without actually having to add each individual number, right? And so here's kind of the standard proof for this. Let's imagine that we had a bowling alley with 6 rows. How many would be there? Well, you might be able to just add the 6 onto this and know that it'd be 21, right? That's saying what's 1 plus 2 plus 3 plus 4 plus 5 plus 6, and we'll just know that it's 21. And by the way, this would look like this in sigma notation. That's an I. But here's another way to do it. What's kind of neat is that 1 plus 6 is the same thing as 2 plus 5 is the same thing as 3 plus 4. It's kind of neat. So let's imagine that we just take the big number. Let's call it B. Well, how did we get to 21 from that? Well, we added 1, because 6 plus 1 is the 7 that we needed. Basically, we're getting 7 times 3, right? And we times it by 3. How did we get 3? Well, that's just 6 divided by 2, right? Because we used 1 line for each 2 numbers. So let's just say big number divided by 2. All right? Seems common sense. Let's try an odd number, though. What happens if we wanted to have a bowling alley with just 1 through 5? Oops. Well, we couldn't do this, right? Because we'd be left over with this 3 in the middle. So here's a trick. What if we just added a 0? Which doesn't affect it at all. Well, that'd be 5 times 3, which would be the big number. And we're not adding the 1 this time. But how did we get 3? That's just 5 plus 1 divided by 2. And let's see if that works with, I don't know, 7. So in this example we have 7 times 7 plus 1 divided by 2, right? Because it's 7 times 4. Okay, so you might think, oh man, this is complicated. I got to remember the odd equation, and I have to remember the even equation. But algebraically, these are the exact same thing. In both of these cases, you're just saying, b times b plus 1 over 2. And by the way, b in standard notation for sigma is just the n. So n times n plus 1 over 2. So that's your standard proof for this, or at least the one I've seen most often. To help students understand how to do this, you're basically just taking 1 and putting it up there, 2 and putting it up there, 3 and putting it up there, so you get 3 even rows of 7. Which, by the way, if we wanted to apply that to this more complicated problem here, that would just be 200 times 201 over 2, which is 40,200 divided by 2, or 20,100. But here's where I'd like to make it a little bit more intuitive for you. I'd like to use Legos. And by the way, you can do this on your own. I think it's kind of neat with Legos if you take your standard one, standard width, or height, I guess, and you add 2 flats, you get a cube, or something really close to a cube. It lines up really well. So with that, you can kind of create shapes that allow you to work with summations, which I'm sure is what Lego had in mind when they created these. So let's do kind of a simple one. Let's imagine that this is 1 unit, and that's 2 units, and that's 3 units. And again, to imagine this, let's imagine that we had a bowling alley with just 3 rows. Well, imagine that we just kind of reorganized those pins and moved everything over to the left so that we had look like that, right? And that's what this is. 1 plus 2 plus 3. So we wanted to really quickly figure out how many pins are in there. And of course, with this small of a number, we could figure out, well, it's 6. Or we could count 1, 2, 3, 4, 5, 6. But what's kind of neat is that you can do this. What if you had 2 of these shapes? And you did this. Well, then you have a really easy shape to figure out, right? This is a rectangle, so we just take length times width. 1, 2, 3 times 1, 2, 3, 4. That's 12. And then in order to figure out what this is, we just divide it by 2, right? So 12 divided by 2 is 6. I could count them, or I could just imagine that I had 2 shapes, like side by side, made a perfect shape, and then divided it by 2. Which is exactly what this equation is saying. Let's take the big number, 1 plus 2 plus 3. Let's take the big number. Let's imagine that we had another shape right next to it, and it made 3 times 4, and then we just divide it by 2, and that gives us the number. And this works with really any. Well, assuming that I have both pieces. Here it is. So let's imagine I'm trying to figure out 1 plus 2 plus 3 plus 4, which remember is the bowling alley. We know this is 10. Well, 4 times 5 is 20. That gives us a really easy shape. Divided by 2 is 10. And it works with really small ones too. If I want to figure out what 1 plus 2 is, that's 3 obviously. That's 2 times 3 is 6 divided by 2, 3. And if I had a really huge one, right, if I just kept going and going and going, and instead of stopping at 4, 1, 2, 3, 4, I went up to 200, they would still fit together perfectly into this great rectangular shape that would be 200 times 201, and then in order to figure out what this is, I just divide that rectangle in half. So that's where I got this from. 200 times 201 divided by 2, well, that's just because the shape would be 200 times 201 divided by 2. And you can do that with a million, a billion, whatever. A million times a million and a one, and million and a one. Million and 1 divided by 2. So hopefully you remember this, or you can think of this when you see this equation, because it's a lot easier, I think, to visualize this way. But yeah, that's it. So I hope this was helpful.